Hello, welcome to my presentation of this paper called QAOA for MaxCat requires hundreds of qubits for quantum speedup. For a longer version that takes under 17 minutes, please refer to the description of this video. Okay, so this paper was published in 2019. They deal with producing a forecast of when QAOA implemented in real quantum circuits will be competitive against classical algorithms. This is the QAOA circuit, or at least one possible way to instantiate it. And then U here are arbitrary three-dimensional rotations in the blocks along the block sphere, and then there are C0 gates in order to produce entanglement. The results are probabilistic. Here is Erwin Schrödinger and his cat. This is the short version of the video, but just note that here I propose just thinking about the circuit as a black box that has parameters that can be twitched. The knobs can be moved in order to parameterize as good as possible, depending on the circuit's depth, of the number of parameters available, a wave function. Here, for the case of one wave function, we need one parameter. Then there was this example of the most general m qubit product state, and the relationship with these, with the relationship of this with the optimization problem of MaxCat, which belongs to the NP complexity class, is by noting that the solution to MaxCat is equivalent to the ground state of the Hamiltonian operator for the Ising problem, where the interaction tensor Jij is equal to the graph's adjacency matrix. The authors then, and in general the community, is able to then approximate this the generated actually ground state by producing a loop that is just performing instantiating the quantum circuit and optimizing it in a semi-classical way. The authors then did the following. First, they generated the problem instance, that is by considering only 3 regular graphs with fixed number of nodes, here for example 8 in A and 4 in B. Then they proceeded to do the gate decomposition, which was just implementing under some set of gates the previously noted most arbitrary 3-dimensional rotation in the block sphere. They used an Intel's paper in order to produce a schedule where they considered actually the underlying connectivity of a grid. Here we can see 3 steps of the scheduling. Then they just produced the bookkeeping operation of just computing an approximation of the metric called the quality of the approximate solution. Then this is the core of the simulation. They set the number of noise gates, which were parameterized using real experimental values of the coherence and amplitude decay characteristic times. And they noted that with 384 noise realizations and 10,000 samples, they were able to approximate, as usual in statistics in experiments, they approximate the expectation value by the sample mean. They then used simplex optimization, and they actually looped this circle. They traveled this loop for a fixed number of times. They fixed the 20, but in general this could be done a variable number of times, and the depth of the circuit could also be a variational parameter. These are the results. They measured a set of points, and they referred to the computational time in seconds under not the time it took to their classical simulation, but they used a linear model for time that takes into account a thing that Aronson generally criticizes from papers. They did take into account both the time required for preparing the qubits and the time required to measure them. They then produced this estimation of the real time that implementing it would take. They fitted it with an exponential function, which it's okay. It's possible to fit any straight line actually with an exponential function with a sufficiently small exponential coefficient. Theirs differ in 10% for the case of depth 4 and depth 8 which also by depth I refer to the circuit's depth, also called step, also called variational hyperparameter. They somehow are fitting these points with an exponential function and not with a straight line, which is here pretty relevant, but then they will use this to produce extrapolation. I guess they're assuming that, this implies that they are assuming that the quantum implementation still belongs to the exponential time complexity class, which is something they specifically mentioned in their paper. They also have the time that the classical algorithm, which was used ACMAXSAT as a benchmark, takes. They fitted the exponential using the asymptotic regime, and they plotted both together. They extended the quantum required time, the computational time for the quantum implementation using the exponential model, where they used confidence bands, 95% confidence bands that can be computed from the goodness of fit, and they extended this forecast in order to claim that several hundred qubits will be required. I just mentioned maybe a few thousand. Then they mentioned the discrepancy of approximately 12% between the exponential factors of the different depths they simulated. It was in green 8 and in red 4. And they noted that if this increase in the exponential factor is actually a trend, then the expected number of qubits in order to have a quantum supremacy will be actually more than a few hundred. That's something they should address in future works, they mention. And finally, they do mention that this step size increasing is actually something as a community consensus. It is expected the parameter p to increase logarithmically with the number of qubits. So those are the two conclusions. First, that QAOA will be time competitive with approximately 1,000 qubits for the special case of max cut in 3 general graphs and simplex optimization, and this observation that it may take even longer. Thank you for your time. More details are available in my PDF, which can be accessed at my GitHub and at the description of this video. Really, thank you for your time.